This talk is about MetaCoq correct, which is about the verification of type checking and erasure for Coq and Coq. And this is joint work with Simon Boulier, Nicolas Tabarot, Yannick, and Theo, who are going to present with me. So it's a non-trivial task to actually verify Coq. Why do we want to do that? So you know that Coq is used to verify programs, to verify hardware, to verify computer theorems that require intense computation that we want to show correct. And Coq is not only used to ensure trust in proofs, but also to produce artifacts out of that. For example, a verified C compiler that's an executable that can be extracted from the concert verified compiler formalization. In the DeepSpec project, there's been the extraction of a web server that's been done in Coq. You can also, of course, extract computer algorithms from proofs, like the four-color theorem gives you a four-color coloring map. Okay. So what do you really trust when you are trusting a proof in Coq? Well, you have this ideal Coq, that is the calculus of inductive constructions, or some variant of it, and we have the actual implementation of Coq. So Coq is based on a theory that's very strong, that has not found, that had not had any problems in the last 20 years. We didn't find any inconsistency in it. And the implementation in Coq is based on the De Bruijn principle, which should implement this theory in a small part of the system that is well delimited that could actually be verified. But what's in there, really? What do you trust? It's a dependent type checker that's been developed over 30 years, about 20,000 lines of OCaml code. It includes a type checker for dependently typed lambda calculus with inductive families, a termination checker, universe cumulativity and polymorphism, an ML-style module system that's been added as well. And there are 3 variants of conversions, which are more and more efficient as you go along the way. And of course, all this relies also on OCaml's compiler and runtime as Coq is implemented in OCaml. Okay. So the actual reality is that this ideal Coq is unspecified in the sense that all these features that were added over the years, we never had a complete specification of how they work together. And of course, that's a recipe for disaster in the implementation, because basically we're specified just by the implementation, and it is buggy when it is actually combining these features. So we have many critical bugs that appear, that usually appear at the boundary of this combination of features like fast computation and universe polymorphism, or when we added the lead bindings to the system, we didn't check everything was going well in the match typing rule, which is very complex. And so we would like to increase trust, and to do that, we will move to this trusted code base, to a trusted theory-based paradigm. So we want to do that by actually formalizing the theory that is implemented by Coq in Coq. So we're going to have a Coq spec of the polymorphic calculus of inductive construction that is going to have a reference implementation verified in Coq. That's what we're going to present today. And all of this is done in the MetaCoq framework, which is a framework in Coq that allows you to verify the Coq terms and define things on them, like plugins. Okay, so this is listing the results that were done in Hall by Könner et al. Or by people in F-star in Apple 2012 to the implementation of Coq. So what we really have, so we are working in MetaCoq. So I'm going to show you source syntax in Coq, but actually what we're manipulating in the system is a verification, so an inductive type in Coq called term, which has constructors for all the constructs of the language. And we can have fixed points. We can have matches. We handle universes and the cumulative hierarchy of universes, universe polymorphism, the ability to abstract on universes, inductive types and inductive families in general, and lead bindings, which are a bit different from usual lead bindings. So in dependent type theory, you can unfold this lead binding value when type checking the body of the let, which is necessary in this case where we apply a typecast. Okay. So what we don't have is the notion of eta conversion, which was added about 10 years ago in Coq. And actually, it's an open problem to say if we have subject reduction for eta conversion with cumulativity and that reduction. We don't implement either template polymorphism, which is another way to do universe polymorphism that is subsumed by cumulative polymorphic inductive types. And finally, we didn't try yet to tackle the module system. Also, we are looking only at what's happening in the kernel, so we do not formalize existential variables or name variables, which are only used outside the kernel in the proof mode of Coq. So let's look at an example of the specification, here reduction. So as I said, we have let bindings in the context, so you can define an inductive relation that tells you how terms reduce in Coq under a certain context. So here I can unfold the body of a variable. We have a general notion of substitution, called binding substitution, if you will, in the system. So you have the usual let reduction rule. And as we have strong reduction, we can also reduce under the body of a let without reducing it, just adding the binding for the let inside the context and reusing the first rule to expand that body in the term. And there's, of course, a lot of other rules for all the reduction rules of Coq on matches, etc. We also have formalized a notion of weak call-by-value evaluation, which is just a standard evaluation in lambda calculus, where we have closed value substitutions and only one reduction for the let bindings. And we can show that this relation is actually included in reduction in empty context. So what have we proven about this specification? So all the structural properties of typing, cumulativity, and reduction are proven. So we have substitution, local and global weakening, which is a bit complicated by the fact that we have these universes and this global graph of universes. And also polymorphic constants that are instantiated by universes. We prove a variant of confluence on this calculus, which uses the technique of Takahashi of a triangle operator, which we actually extend. So when you see this reduction rule for let, actually what you need to do to prove confluence is show that you can reduce in the context and the term at the same time, and you can prove confluence by reduction in parallel in the context and the term. Okay, and also we have like standard inversion principles that you get on dependent type series. So we've not done all the work on formalizing Coq yet, so we have some assumptions that the rest of the work is based on. So of course you have to believe in the specification of typing, reduction, and cumulative that we gave, but it's relatively small. It's about 500 lines of OCaml code, Coq code, sorry. We didn't tackle the strict positivity and guard condition criterions. We just have oracles right now, which allows us maybe in the future to implement the guard condition or to move to another system like size types. We have ongoing proofs of subject reduction and validity. It's just very complicated due to the representation of inductive types in Coq to work them out completely. And so they should not be assumptions in the future, but we have to assume strong normalization. Thanks to Gödel incompleteness, we cannot prove strong normalization. We're going to use that assumption of strong normalization to be able to verify the type checker, as Theo will tell us.
Okay. So how do you define a verified type checker inside Coq? So what you want to do first is to be able to define a notion of reduction. And you might assume that this is something that's going to be easy since we assumed strong normalization, but it's not. So basically we want to take some input u term and output some v that is a reduct of it. Okay. This is, so we're not confusing stuff. Here u is a term, like in the AST of MetaCoq. V is a term as well, and the reduction is a proposition. So in Coq syntax, it would look like something like this, using a sigma type to combine the term v and its proposition. In order to do to prove it to be terminating, we actually rely on strong normalization, but also on some order that's a bit more involved. So we allow to go under subterms. So here we have pi1 and pi2 that represent the surrounding terms that we're considering, and the thing that we prove is that the whole term reduces to the whole other term. Okay, so let's consider an example first. So let's say I want to reduce t of u, t applied to u in some context. Okay, so the first thing you do is you want to focus on t and do a recursive call on this. And let's say for some reason that t reduces to the identity function, maybe it's a definition. So you can plug it in and start again. This is possible because where lambda xx is indeed a redux of t, so it's smaller. Here, lambda xx is already a weakened norm form, so we can consider its surroundings, and we see it's applied to u, so we can consume it and do a recursive call on u. Again, this is something that's valid because t of u does reduce to u, so it is smaller. If we want to do the same thing with pattern matching, we will focus on the M, like the scrutiny of the match, try to see if it reduces to some constructor, let's say some S of B, and then we would just try to reduce the corresponding branch. So here we actually need the function to be correct by construction to be able to do the recursive call. Okay. Now that we have our notion of wicket reduction, we can go and deal with the conversion. So just to be quick, the specification of conversion is quite simple. We just say that two terms are convertible if they basically reduce to alpha equal term. And now we want to do an algorithm that deals with conversion the same way Coq does. So we're taking some u of type A and v of type B, and we want to decide if u is convertible to B. Actually, we're not proving that it is decidable. We're just proving that in some cases we say, well, they're convertible, and maybe in some of the cases we just return an error. So the completeness of this algorithm is some future work. Again, this is operating on syntax, so we're considering u and v of type term, and we're assuming that they're well typed. Okay. So how we're doing this is we're first reducing both terms using the wicket reduction that we defined before, and then we're trying to compare the both of them. Like for instance, if they're both lambdas, we want to compare the two domains, and if they are indeed convertible, then we want to compare the bodies. This is again something that's possible because the domains are subterms of reducts of the original terms, and the other cases go somewhat the same way, like for pi types, and so on. So there are actually some more tricks. This is a very simplified presentation, and the algorithm needs actually, for the termination of the algorithm, we need 5 different orders that are connected together with a dependent lexicographical order modulo some bisimulation. So it's a bit complicated, but it works. So we have wicket reduction. From it, we derived conversion. We actually derive cumulativity, but I don't go into the detail. We use a variant of the Bellman for algorithm in a modular way, so we can actually plug in any algorithm for checking cumulativity of universes that would be more efficient. And then from it, we can get to inference of type in a pretty straightforward way, which then allows us to do some type checking. So like just pretty easy. We just say, if we want to check T as type A, we infer the type of T to be some B, and then we check that B is indeed a subtype of A, and if so, then we're happy. Okay, but so now that we have this algorithm written in Coq, we wanted to be able to extract it to run this separately and actually check Coq terms. At first, the extraction didn't work because of some bug in the extraction mechanism, so we had to change the definition for it to work. But that is a good motivation for us to actually verify this extraction mechanism.
So Coq implements an extraction mechanism. It was done by Pierre Letouzy already 15 years ago, and you can take Coq definitions and turn them into OCaml definitions automatically. And the first step of this extraction mechanism, which can be written down on paper very well, is that you erase all types and terms in your programs because they don't matter in OCaml. And that's exactly what we're implementing. So we're implementing an erasure function, which takes terms from the abstract syntax tree of Coq and goes to an untyped lambda calculus, which will still have match and cofix and fix. It also has this box thing here, which says this was a computationally irrelevant term, so this might have been a proof. And then type and proof erasure, if you apply it to a type, will return the box, or if you apply it to a proof, will return the box. If you run it on the example from the beginning of reversal on vectors, you will lose all the type informations, and you will lose the proof that was used in coercing the type of the vector around, because you don't care about this in OCaml. What makes the verification of this tricky is that in Coq you can escape propositional contents to type contents under the singleton elimination principle, and that makes the whole proof involved. Otherwise it would be a pretty easy simulation proof. So for instance, if you're erasing on a big match, which is matching on a proof, and returning a computation, in the end what you want to do is you want to disregard the match because you were matching on something that you don't care about and just go on. But proving the correctness of this is the tricky part. So if you apply erasure to coercion, in the end what you will have is that this is the identity function because you don't care about proofs. And in the end you will have that the erasure of reversal on vectors is essentially what you would write for lists because you have lost all the typing informations. You have some natural numbers around that you don't really use in the computation. What we prove for erasure is the following. We prove a correctness theorem which says that if you have a Coq term t in the AST and you call by value reduce it to v and you can erase it to t prime, then t prime will also call by value evaluate to a v prime, which is somehow observationally equivalent to v. And in the end, what you then have is if you have a natural number, a term which is typed as a natural number in Coq, then we know by strong normalization and canonicity that this will reduce to a numeral. This will also mean that call by value reduces to a numeral, and then by the correctness theorem, we know that the erasure of Coq of the erasure of this term will also reduce to the right numeral. All right. So what do we end up with? In the end, we have a specification of Coq written down as an inductive proposition in Coq. We have a Coq function implementing a verified type checker for exactly this specification, all done in MetaCoq, which is implemented in Coq. In the future, the idea would be, or we can already do this partially, so we already have a Coq command where you can say MetaCoq check something for me, please. And then it will not use the Coq type checker, but the MetaCoq type checker that we have implemented to type check a term. And so in total, this is about 23,000 lines of specification with about 40,000 lines of Coq code. And the same you can do for erasures. You can also run erasure interactively in Coq. You can use this for lots of things. So there's already ongoing work on the 30-Coq compiler, which compiles essentially MetaCoq terms down to C, which is using our type and proof erasure function. So by this, we will in the end get the verified Coq compiler. We would like to look at other things in the future. So for instance, in order to extract what we have written to OCaml in a verified way, we need full extraction to OCaml verified. That would be an interesting project in the future. Also more theoretical things, like we can now build verified models for the underlying theory of Coq, say a set theory, say realizability models. All right, all of this code is online. It's an ongoing work on GitHub to develop several branches of all of this project. We're very happy for contributors, and we're happy now to take your questions.
This is fantastic work. So I saw you omitted the module system, which is so unfortunate because it's a fantastic piece of Coq. But if you were to consider that, would you make a formal spec of the current module system, or would you make something maybe better?
So we're rather thinking about elaborating the module system down to a simpler system based on dependent sigma types, simply.
That sounds better, yes.
Yeah. And actually, we can already check terms that are built from modules, because we just look at the expansion of the modules of the functional applications, for example. So it's not, in practice, it's not such a big problem to actually use it, but of course it would be nice to have a verified.
All right, so now you basically expand all of the modules and then you type check that.
Yeah, and actually the checker, the Coq checker, which is not Coq-C, but Coq check, does the same. It looks at the expansion.
Okay, I did not know that. Thanks.
So I wonder whether you guys are planning to generate a .vo file that can be independently checked by this ideal Coq or not?
It's a matter of engineering. I mean, we could actually write a standalone program now that checks the VO files.
Are there any features that currently in .vo files that falls outside your verified code?
Yeah, so the ETA conversion, template polymorphism, and modules.
Okay.
It's a bit unfortunate for template polymorphism because it's actually used in the standard library. Okay. So what we do check, I mean, we have running examples now of the hot library, which is not using this old feature, but rather using cumulative polymorphic inductive types, which we can check this way.
Okay, we have a question from Slido. What are your ideas for how to prove the syntactic guard condition for fixed points correct?
So there are many possibilities. One that looks very enticing is just to first do a refinement step where we move from the syntactic guard condition to an annotated variant of the calculus using size types and rely then on the size types correctness. That looks like the most promising and feasible way.
Cool. I have a question too. Have you considered proving strong normalization for a system, say, with limited universes? Just two, maybe.
I haven't. I'm happy to work with someone who tried to do that in Coq. Yeah.
Any other questions from the audience? Well, okay, we do.
Could you say more about the verified models, what you mentioned on the last slide? Is it connected to the work by Bruno Boas?
I think we haven't started yet, but if we start, it will be strongly connected to by the work of Barras. Maybe the first step is actually to look what he's doing and more or less verify it literally in Coq.
Thank you.
Have time for a couple more questions, maybe? Oh.
So we do not treat it yet, but it should not be too hard to treat, even with the on-type conversion. I mean, the S-prop sort was actually engineered so that we could do a purely syntactic proof of subject reduction with it, so it should work.
What about the efficiency of the type checker that you have implemented? Would it be able to type check developments, let's say like Iris or CompSort or Rust Belt?
In the future, yes. So right now we can check medium-sized developments. It's not too bad actually, the code that is extracted.
So what are the main challenges to?
So there are mainly representation challenges because we have a very poor treatment of strings representation in the AST of MetaCoq that we extract. We can hack the extraction to extract to a list of characters, for example, but a good extraction for that would already improve by an order of magnitude the performance. And that's the main thing.
All right, I guess this brings us to the end of the last session of POPL. I invite you to thank our speakers again. Thank you.